Look up at the night sky and you see matter. Stars, dust, the cold geometry of empty space. But modern physics whispers a stranger truth. Beneath the atoms and the light, beneath gravity itself, there may be something more fundamental than any particle. Not a substance, but a process. Not a thing, but a computation. This is the digital cosmos, a universe that does not merely contain reality. It calculates reality bit by bit into existence. For centuries, we treated information as something abstract. A thought, a number, a ghost, with no mass, no location, no cost, but that intuition was wrong. Information cannot exist on its own. To record a single fact, you must arrange matter or energy in a specific way. A magnetized domain, a charged transistor, an electron spin pointing up or down. Information is always written into the physical world. It has weight, it has consequences, it is physical. Reduce any message to its essence and you reach the bit, the simplest possible distinction. Yes or no, on or off, 1 or 0. To store that single bit, you must push some physical system into one of two states and hold it there against the relentless chaos of thermal motion. The bit is not a symbol floating in a void. It is a configuration of reality itself, etched into the binary substrate from which all complexity is built. Thermodynamics gives us the language for this. Any physical system has countless microscopic arrangements, its microstates, hidden beneath the properties we can actually measure. When we store information, we constrain those possibilities. We force the system into a smaller set of allowed states. Knowing a bit means the system can no longer be just anything. It must be this or that. To compute is to reduce the universe's options, narrowing a vast space of possibility towards certainty. In 1961, a physicist at IBM named Rolf Landauer asked a question almost no one thought to ask. If information is physical, does processing it cost something real? He discovered that the answer had been hidden inside thermodynamics all along. Computation, he realized, is not free. Every logical operation that destroys information must pay a price set not by engineering, but by the deepest laws of nature. With one insight, Landauer welded the world of bits to the world of heat. Landauer's principle sets an unbreakable floor. To erase a single bit of information, you must dissipate a minimum amount of energy. Boltzmann's constant multiplied by the temperature multiplied by the natural logarithm of 2. At room temperature, that is roughly 3 zeptojoules, 3 billionths of a trillionth of a joule, vanishingly small, yet absolute. No technology, however advanced, can erase a bit for less. This is the Landauer limit, the toll booth of erasure. Why must erasure cost anything at all? Consider what deletion truly means. Before, your system could have held a 1 or a 0, two possibilities. After erasure, it holds only 0, a single possibility. You have shrunk the system's microscopic freedom, but the second law of thermodynamics forbids you from destroying that freedom for free. The entropy you removed from your data cannot simply vanish. It must be paid in full, exported elsewhere as a thermodynamic toll. Here lies the strange asymmetry at the heart of computation. Reading a bit costs nothing in principle. Copying it, moving it, even running it through reversible logic. All of this can be done in theory without any waste at all. The price is charged only as a moment of forgetting. Creation is cheap. Memory is cheap. It is deletion, the act of throwing knowledge away, that the universe refuses to subsidize. This is the bit deletion paradox. When you erase a bit, the entropy of your data falls by the logarithm of 2. But the total entropy of the universe can never decrease, so nature performs a shift. The order you impose upon your memory is balanced by an equal disorder pushed outward into the surroundings. Entropy is not destroyed, it is relocated. Every clean ordered 0 you write is purchased by a corresponding increase in the chaos of the world beyond your machine. And that exported disorder takes a familiar form. It lives as heat, the random molecular motion radiating into the environment. This is why your laptop grows warm, why data centers must be cooled by rivers of chilled air. Every deleted file, every overwritten register releases a faint pulse of thermal energy. Multiply that by the trillions of operations happening every second, and computation becomes a furnace. Information processing is quite literally a thermal emission vector. The root of the cost is irreversibility. Most logic gates we use destroy information given only the output. You cannot reconstruct the input. That lost history is precisely what must be paid for in heat. There is a loophole, reversible computing where no information is ever erased, and in theory no energy need be lost. But our universe as it actually runs is built upon irreversible logic, and so it is forever generating heat as it sinks. Now we ascend from the machine to the cosmos. The physicist John Archibald Wheeler, who named the black hole and mentored a generation of giants, spent his final decades chasing one audacious idea. He suspected that the bedrock of reality was not matter, not energy, not even space-time, but information itself. Everything physical he proposed emerges from answers to yes or no questions posed to nature. Existence in Wheeler's vision is a vast lattice of resolved binary choices. He distilled it into three immortal words: it from bit. Every particle, every force, every grain of space-time derives its very being from bits, from the binary outcomes of quantum measurements. Reality is not a stage on which information plays out. Reality is the information. When a quantum system is measured and a definite answer crystallizes from a cloud of possibility, a bit is born, and with it a fragment of the physical world. Think of it as software and hardware. The matter we touch, the stars, the planets, our own bodies, is the user interface, the display. It is what the cosmic computation renders for us to perceive. But behind the screen runs the real program, the relentless processing of quantum information. The hardware is woven from the fabric of spacetime itself, and what we call physical law is simply the operating system dictating how each bit transforms into the next. And the bits of this cosmic machine are not ordinary. They are qubits, quantum bits, capable of holding 0 and 1 at once, entangled across impossible distances. Some physicists now suspect that space-time itself is stitched together from entanglement, that the geometry of distance and the very pull of gravity are woven from the correlations between quantum bits. Pull the threads of entanglement apart, and space may simply dissolve. Geometry perhaps is entanglement made visible. If this is true, the implications are staggering. The universe does not store its state in some external memory. The universe is the memory, a colossal quantum register, the size of the cosmos, ceaselessly updating itself. Each interaction is a computation, each moment a clock cycle. The galaxies wheeling overhead are not merely objects in motion. They are data flowing through the registers at the core of reality, processed by the oldest computer that has ever existed. So let us take the metaphor at its word and ask the engineers questions. If the universe is a computer, how fast can it run? How much can it remember? Every processor, no matter how exotic, obeys hard physical limits, ceilings imposed by the speed of light, by quantum mechanics, by the finite energy at its disposal. The cosmos is no exception. Even an infinite seeming sky has a maximum clock speed and a finite capacity to compute. The first ceiling comes from Hans Bremermann, drawing on Einstein's mass-energy equivalence and Heisenberg's uncertainty principle. He derived the maximum rate at which any physical system can process information. The answer is breathtaking. A single kilogram of matter could in principle perform around 10 to the 50th operations every second. The energy locked inside ordinary mass is a computational reservoir of almost unimaginable depths, if only it could be fully unleashed as raw processing power. Push this to the extreme and you reach the ultimate laptop, a hypothetical machine that converts all of its mass into pure computation. Its speed is set by the Margolis-Levitin theorem. The more energy a system carries, the faster it can flip between distinct states. Pack enough energy into a small enough volume and you approach maximum computational density. But push further still and the matter collapses under its own gravity into a black hole, the densest computer physics will allow. The collapse reveals the second ceiling, the Wittgenstein bound, the absolute limit on how much information can fit inside a region of space. Astonishingly, that limit scales not with the volume enclosed, but with the surface area of its boundary. A black hole stores its entire informational content on its event horizon, roughly 1 bit for every 4 squared time lengths. Reality, it seems, is fundamentally holographic, written across surfaces rather than packed into depths. Apply these laws to everything we can see. The physicist Seth Lloyd ran the numbers for the entire observable universe. Since the Big Bang, the cosmos could have performed at most around 10 to the 120th logical operations, acting on no more than 10 to the 90th bits of information. Enormous but finite. The total bit capacity of our universe is a fixed knowable quantity, and anything finite can, given time, be filled completely. Here the story turns dark. If the universe is computing, then every event is an operation. A star fusing hydrogen is running a calculation. Two black holes spiraling into collision are crunching numbers on a scale no machine could match. A single cell dividing executes a program written in chemistry. Reality never pauses, it computes without rest. And as we have learned, every irreversible step in that computation must pay its thermodynamic toll in heat. That heat is not harmless to a computer. Heat is noise, the random jostling of particles that corrupts delicate states and threatens to flip a 1 into a 0 by accident. The hotter a system grows, the harder it must work to keep its data intact, and the more energy it burns doing so. The universe faces the same predicament. Its own waste heat slowly fills the space around it, raising the floor of thermal noise everywhere. And the heat has nowhere to go. A laptop dumps its warmth into the room. A data center vents it to the open sky. But the universe has no outside, no cooler environment to absorb its exhaust. Every bit ever erased by every process across cosmic history adds to a rising tide of entropy with no drain. The cosmos is a sealed machine running flat out, its thermal output accumulating toward an inevitable data overflow crisis. This is the second law, restated in the language of computation. The change in entropy of the universe is always greater than or equal to Boltzmann's constant times the logarithm of 2. For every bit the cosmos forgets. Entropy can only climb. And entropy is also a gradient, the very slope that allows anything to happen at all. Useful energy flows downhill, from order to disorder. Every computation flattens that slope a little further toward equilibrium. So picture the universe as a code decay engine. It runs by spending the difference between order and chaos, converting structured energy into useless heat with every operation it performs. The stars themselves are temporary, magnificent processors, burning through their fuel, destined to dim and die. With each calculation, the cosmos erodes the very gradient that powers it, computing itself inexorably toward a state where no further computation is possible at all. Trace this forward across unimaginable spans of time. The stars wink out one by one. The galaxies drift beyond each other's reach. The black holes, the last great engines, evaporate into a faint mist of radiation. The cosmic computer approaches maximum entropy, a uniform, lukewarm bath, where every region looks like every other. Its registers are exhausted. Every gradient spent energy still lingers, but none of it can do work. The machine has run out of room to compute. A computer that fills its memory faces a brutal choice. It must either halt entirely or begin overwriting what came before. And so a haunting question arises. Is the expansion of our universe a kind of overwriting, stretching and diluting the past, smearing yesterday's information so thin that it can no longer be read? A space swell structure is erased. Perhaps the cosmos buys its future only by deleting its memory of all that has been. Imagine then. The final system delete. The last star has gone cold. The last black hole has surrendered its mass to the dark. Somewhere, in the unfathomable depths of future time, the very last bit of usable information is erased, paying its tiny tithe of heat into a void already saturated with it. With that one last deletion, the universe completes its final operation. There is nothing more left to compute, and nothing left to remember. But is deletion truly the end, or a reset? Some cosmologists wonder whether a universe wiped clean of all information, smooth and featureless and maximally disordered, becomes indistinguishable from the blank, formless state that preceded our own Big Bang. If maximum entropy looks like a fresh, empty page, then perhaps the heat death is not a tomb but a reboot, the system clearing its memory and waiting, somehow to begin its calculation anew. And consider what becomes of time. Time, as we feel it, is the direction of rising entropy, the arrow that points from an ordered past toward a disordered future. But in a universe drained to perfect equilibrium, entropy no longer changes. With no gradient left to climb, the arrow loses all meaning. Time itself lifts away, dissolving into a stillness where before and after can no longer be told apart. The clock does not stop, it simply ceases to mean anything. What remains is the timeless zero. No structure, no memory, no flow of moments. A cosmos that has forgotten everything it ever computed, returned to a blank slate of pure, featureless potential. It is the same silence from which we may have first emerged, eternal, motionless, holding no information at all. In the end, the universe does not explode and it does not collapse. It simply erases itself, fading gently back into the perfect quiet of nothing. And so the great computation comes full circle, from the first bit flickering into being, to the last bit dissolving into the dark. We are fleeting patterns in that calculation, brief eddies of order swimming against the current towards zero. Perhaps that is what makes this moment precious. We are the universe, computing itself, aware of itself, before the memory fades. If this journey moved something in you, subscribe and stay with us, while the cosmos still remembers how to dream.